Good morning, students. Welcome back to finite element analysis classes. And today is class 5 of module 3. In this class, we will be discussing about analysis of shafts. And in the previous classes, we have discussed the same analysis of beams. In continuation of this one, here also we will be discussing about the analysis of the shafts. And in general, what is a shaft? A shaft is a rotating member, usually of circular cross section, which is used to transmit the power or motion. This is a brief definition of the shaft. And the shaft, which provides the axis of rotation or oscillation of elements such as gears, that is a mechanical element such as gears, pulleys, flywheels, cranks, and the shaft also controls the geometry of their motion. This is the introduction to what is a shaft. And the major element for any power transmitting element or power motion transmitting element is the shaft. So the major necessary of the shaft plays a vital role in majority of the mechanical components. And now the important thing is to study the shaft. How does it behave under loadings? And the loading, either it may be torque or either it may be a physical loading. Now, because of the loading conditions, the torque is subjected to a deflections. There is a deflection in the shaft, and along with that one there is a slopes. Because of the axial loads, there is a slopes that will be developed in the shaft members. So this deflection and slopes are a function of inertia, that is a load inertia, and in turn the inertia is a function of geometry. The shaft may be designed on the basis of the strength or on the basis of rigidity and stiffness. So to design any shaft, these three parameters are most important: the strength, rigidity, and the stiffness. Now, in designing of any shaft, there should be considered certain considerations, and the considerations which will be based on the strength, and the strength based upon the strength with the following certain conditions. Let us discuss those conditions. The conditions is that if the shaft is subjected to twisting moment only, whether the condition is, the first condition it may be at whether the shaft is subjected to twisting moment only, pure twisting moment. Because of pure twisting moment, what is the stresses developed in the member, what is the what you call as rotations and deflections in the member. And the second condition is that whether the shaft is subjected to bending moment only. First condition is only twisting moment, and the second condition is if the shaft is subjected to bending moment only. The third condition is that whether the shaft is subjected to combined twisting moment and bending moment. When these two, what you call as movement, twisting moment as well as bending moment is subjected, then considering this type of a problem, we need to analyze the problem. And the fourth one is whether the shaft is subjected to fluctuating loadings. That is not a regular loading, that is uneven loadings, and the loadings are repeated. In these conditions, the whatever the designing of the shaft will be based upon these conditions. Now, this is the whether the designing of the shaft will be taking place based upon these four situations or these four conditions. Now, to solve a problem, to analyze a problem by using our finite element method. So, there is a necessary to have a finite element formulation for the shaft. So, in our module, in this topic, we will be discussing how to formulate the finite element equation for these shafts. So the topic here for your syllabus is finite element formulation of shaft. So here we will be considering a circular shaft in terms of, we can consider it as a prismatic bar. Now let us consider this prismatic bar or rod of cross-sectional area capital A, and which is subjected to a twisting moment capital T. which is shown in figure. That is the first figure which is subjected to a twisting moment capital T. Let subjected to a twisting moment capital T, and let the rod is modeled as one dimensional bar element. The bar, we can consider the look into the second sketch. The bar is considered as one dimensional bar element having two nodes, and these two nodes is node 1 and node 2. At node 1 we have the twisting moment as T1, and because of this twisting moment we have the end twist, that is T1, and the length of the element we will consider it as L. And similarly at node 2 the end torque is T2 and the end twist is theta 2. That is what let T1 and T2 are the end torques at node 1 and 2 respectively. And due to this torque there is a end twist, and these twists will be theta 1 at node 1 and theta 2 at node 2. Now assume a linear angle of twist, which is varying along the x-axis of a bar such that theta is equal to a1 plus a2x. Let us consider the equation, that is a linear equation, thus theta is equal to a1 plus a2x. For this equation we will be applying the boundary conditions, and we get the twist theta is equal to n1 and n2, matrix of n1 n2 into the vector as theta 1 and theta 2, where n1 is a safe function which can be written as x2 minus x divided by x2 minus x1, and n2, the second shape function n2, can be written as x minus x1 divided by x2 minus x1. Now the relationship between the shear strain gamma and the angular twist theta can be obtained by the torsional deformation of the bar segment. So because of the bar segment we will assume a radial line OA. In the first sketch you assume the radial line OA which remains straight, because this is an assumption. We need to consider that the layers, whatever the twisting layers, will be remaining in a what you call a straight during twisting and torsional deformation. So we will assume a radial line OA remains straight during twisting or a torsional deformation. Now look into the sketch here. In the sketch we will assume the arc length AB. Let us assume the arc length AB is given by, this is the arc length, you can assume here the arc length AB we will assume it as AB is equal to gamma max into dx, where gamma is the maximum that is a shear strain into dx, that is equal to r into d theta, where capital R is the radius of the shaft, and theta is a small angular deformation. Now for this one we have the maximum shear strain is equal to r into d theta by dx, because we have the arc equation, that is maximum deformation gamma max is equal to r into d theta by dx, that is the angle of twist is varying along x-axis or along the length of the bar. Similarly, at any radial position or distance r, at any radial position small r, from similar triangles OAB, from the sketch, you look into the sketch, OAB and OCD, we have the shear strain, that is a gamma is equal to r into d theta by dx, and where d theta is a change in the angular twist, that is theta 2 minus theta 1, and so gamma is equal to r by L into theta 2 minus theta 1. Let us consider this as equation 1. Also, for linear elastic isotropic material, the shear stress tau and shear strain gamma can be written as tau by gamma is equal to G, where G is the rigidity modulus. Let us consider this equation as equation number 2. Now, from torque equation we have T by J, the torque equation we have T by J is equal to tau by R, and we can rewrite the equation to obtain the torque T is equal to tau into J divided by R. Let this equation be equation number 3, where J is the polar moment of inertia and tau is the shear stress of the particular material and R is the radius of the shaft. Now, considering the above equation, we can write the torque equation T is equal to Gj divided by L into change in the angular twist, that is theta 2 minus theta 1. From figure, at node 1, let T be T is equal to T1, that is twisting torque at node 1. Then if torque is T1, then we can write the equation, the above equation T1 is equal to Gj divided by L into T1 minus T2, where T1 minus T2 is the change in angular twist at node 1, that is theta 1 minus theta 2. Let this equation be equation number 4. Similarly, at node 2, let T is equal to T be theta 2, that is T be as T2 at node 2. Now considering this one, we can write the torque at node 2 T2 is equal to Gj divided by L into theta 2 minus theta 3, where theta 2 minus theta 3 is the angular displacement at node 2. Now let this equation be equation number 5. Now, writing the above equation 4 and 5 in matrix form, we can represent the two equation number 4 and equation number 5 can be represented in the matrix form as, that is T1, that is a matrix of T1 and T2 can be written as T1 and T2 is equal to Gj divided by L into 1 minus 1 minus 1 1 into the displacement, that is the angular displacement theta 1 and theta 2, vector theta 1 and theta 2. That is, we can represent the equation as, that is matrix T is equal to K into matrix K into matrix theta. See, this one is similar to the whatever the equilibrium equation which we have written for a bar problem, that is equal to KQ is equal to F. Similarly, here we will be writing KQ is equal to T. In spite of force, we have the torque equation T. So, here where K is the stiffness matrix of the torsion bar, where K is the stiffness matrix of the torsion bar, and theta is the angular displacements, and this stiffness matrix can be written as Gj by L into 1 minus 1 minus 1 and minus 1. Look into this equation, that is K is equal to Gj by L into 1 minus 1 minus 1 and 1. This is similar to the equation which we have taken for a bar problem. In a bar problem, we have taken as EI, AE divided by L. Now, in spite of this one, we will be taking it in a torsion, in a shaft problem, we will be considering Gj by L into 1 minus 1 minus 1 and 1, where G is the rigidity modulus and J is the polar moment of inertia and L is the length of the element. So here, this is the stiffness matrix. This is a derivation for a stiffness matrix for the torsion of bar. Now considering this equation, we need to analyze certain problems, that is how the bar is behaving under the torque or under the loading such as the twisting moment, how the bar is deforming and what is the deformation in the bars, considering either it may be a simple uniform bar or it may be a stepped bar. So this is the important equation or derivation where we need to solve the element stiffness matrix for a torsional member or a torsion bar. Remember this equation or remember this equation and derivation for solving the problems. Now let us look into the problem, that is problem 1. Here we have a stepped bar or a stepped shaft, a circular bar of circular cross section, a solid bar of circular cross section shown in figure is subjected to a torque of 1 kilonewton meter at its free end and a torque of 3 kilonewton meter at its change in cross section. Determine the angle of twist and shear stress in the bar. And the data is given Young's modulus as 2 into 10 raised 5 Newton per mm square and rigidity modulus as 7 into 10 raised 4 Newton per mm square. Now look into the sketch. Here the solid bar, that is a stepped bar, the left end of the bar which is having 100 mm diameter and a length of 200 mm. The second bar which is of 50 mm diameter is 400 mm length. And a 300 kilonewton torque is applied on a 100 mm diameter shaft and other 1 kilonewton torque is applied on a smaller diameter shaft. So for this problem, we need to analyze what is the angle of twist. That is, what is the twist in the sense theta 1 and theta 2. That is the angular deformation theta 1 and theta 2 we need to determine. To determine this one, we will go with the steps which will be followed in the FEM. Now the first step is to formulate the finite element model. So since we have the model as two bodies or two solid bars, one is having 100 mm and other one is 50 mm. So we will be considering this as there are two elements. So we need to convert the physical model to finite element model. And the finite element model which will be having two elements, that is element 1 and element 2. Element 1 is connected between node 1 and node 2. And for element 2, the nodes are 2 and 3. At node 1, the torque is T1 and the angular twist is theta 1, and at node 2, the torque is T2 and the angular displacement is theta 2, and at node 3, theta 3 and T3 and theta 3. First element is having a length of 200 mm and the second element is having a length of 400 mm. This is first step. Second step is to write the element stiffness matrix for a shaft or a shaft bar problem. That is, element stiffness matrix for a shaft is K is equal to Gj divided by L into 1 minus 1 minus 1 and 1. Here in the data he has given the rigidity modulus J as 7 into 10 raised 4 Newton per mm square, and J, we know the equation for a solid bar, J is equal to pi d to the power of 4 divided by 32, and this is the data which he has given. Since we are having two elements, so the element stiffness matrix for element 1, that is, we can write it as K1 is equal to G1 J1 divided by L1 into the matrix of 1 minus 1 minus 1 and 1, where G1 is 7 into 10 raised 4 Newton per mm square and J is pi d1 to the power of 4 divided by 32, and that we can write it as 9.82 into 10 raised 6 mm to the power of 4. And substituting these values along with this one, we have the first element length is 200 mm. On substituting the values of G1, J1 and L1, we can write G1 as 7 into 10 raised 4 and J1 as 9.82 into 10 raised 6. It is mm to the power of 4 divided by length. We are considering the same in terms of mm. That is 200 into 1 minus 1 minus 1 and 1. Therefore, retain the power outside and only consider the numeric value inside the matrix. That is 10 raised 9 into 3.44 minus 3.44 and minus 3.44 and 3.44. This is the first element stiffness matrix for the element 1. Similarly, for element 2, the element stiffness matrix can be written as K2 is equal to G2 J2 divided by L2 into 1 minus 1 minus 1 and 1, where G2 is equal to 7 into 10 raised 4 Newton per mm square, and J is pi d to the power of 4 divided by 32, and we answer the value of the second shaft or second rod diameter is 450 mm square, 50 mm. So we have the J is equal to 0.16359 into 10 raised 6 mm to the power of 4, and L2 is equal to 400 mm. And substituting the value of G, J and L, we have the second element stiffness matrix K2 is equal to 7 into 10 raised 4 into 613.59 into 10 raised 3 divided by 400, that is the length of the second element, into 1 minus 1 minus 1 and 1. And we now retain the power outside, that is the power is 10 raised 9 into 0.107 minus 0.107 and minus 0.107 and 0.107. That is the element stiffness matrix for second element. Now considering two element stiffness matrix, we write the global stiffness matrix, that is K is equal to K1 plus K2. Now let us combine the element stiffness matrix of element 1 and element 2. K is equal to 10 raised 9. When we combine, we have the global stiffness matrix as 10 raised 9 into 3.44 minus 3.44, 0, minus 3.44, 3.547, minus 0.107, 0, minus 0.107 and 0.107. This is the global stiffness matrix. Step 4, we have the global load vector. The global load vector T can be written as T1, T2 and T3. Since there is no any torque at node 1, so we will represent it as 0. Whereas there is a torque at node 2, that is T2 is equal to 3 kilonewton, we will be representing as 3. And similarly T3, torque at node 3, T3 is equal to 1 kilonewton, so we will be considering it as 1. So this is the load vector or torque vector T is equal to 0, 3 and 1. Now step 5 is equilibrium equation. We know the equilibrium equation as KQ is equal to F. Now in this equation we will be writing as K into theta is equal to T. And now we have the global stiffness matrix K is equal to 10 raised 9, 3.44 minus 3.44, 0, minus 3.44, 3.547, minus 0.107, 0, minus 0.107, 0.107 into the vector of the vector displacement, that is the angular displacement vector as theta 1, theta 2 and theta 3. And the loading vector in the sense the torque, the torque vector can be written as, since there is no torque at node 1, 0, and there is a torque of 3 kilonewton at node 2, that is 3, and there is a torque at node 3, that is 1 kilonewton. So here this is the equilibrium equation. And now for this equilibrium equation, to know the unknown displacement, we need to apply the boundary conditions. See, look into the sketch here. The first element, which is having a diameter of 100 mm, is been fixed, whereas there is a torque of 3 kilonewton at node 2 and there is a torque at 1 kilonewton at node 3. So here, since node 1 is completely fixed, that is theta 1 is equal to 0. There is no any angular particular torque and it is completely fixed. There will not be any angular deformation or angular twist. Now considering this one, we will apply the boundary condition. The boundary condition is, since there is no, it is been fixed, theta 1 is equal to 0 at node 1. Now by applying the elimination method of boundary condition for the equilibrium equation. Now let us consider the same equilibrium equation, that is K into Q is equal to F. And here the equilibrium equation, we are again representing the KUs, that is 10 raised 9, 3.44 minus 3.440 minus 3.44, 3.547 minus 0.107, 0 minus 0.107, 0.107, theta 1, theta 2, theta 3. And the torque vector can be written as T1 is 0, T2 is 3 and T3 is 1. Now for this equilibrium equation, we need to apply the boundary condition. Since node 1 is fixed, so we will take it as theta 1 is equal to 0. So for this reason, we will be eliminating the corresponding row and column. Since node 1 is fixed, its corresponding row is eliminated. That is eliminating the first row and first column. Then the size of the equilibrium equation is reduced to 2 by 2 matrix. So on solving these two signs, we have the reduced equilibrium equation as 10 raised 9 into 3.547 minus 0.107 and minus 0.107 and 0.107 into theta 2 and theta 3, that is equal to 3 and 1. Here this is the reduced equilibrium equation. From the above what we call as equilibrium equation, we have two unknowns, that is two unknown equations. We have two unknowns. Because of the two unknowns, we will represent into two equations, and these two equations will be having, and we will be having the unknown deformation theta 2 and theta 3. Theta 2 is equal to 1.162 into 10 raised minus 9 radians, and theta 3 is equal to 1.050 into 10 raised minus 9 radians. These are the unknown deformations, that is angular twist at node 1 and at node 2 and node 3. And in the question, he has also asked to determine what is the stress in element 1 and what is the stress in element 2. Now we know that the shear stress equation can be written as tau is equal to G into gamma, where G is the modulus of rigidity and gamma is the shear strain. And here also we know that the torque equation T is equal to Gj into Gj by L into theta 1 minus theta 2. And from these two above equation, we can write the torque equation as T by J is equal to tau by R. And therefore, the shear stress equation can be written as Gr by L into theta 1 minus theta 2, where G is the modulus of rigidity, R is the radius of the shaft, and L is the length of the shaft, and theta 1 minus theta 2 is the change in the angular deformation. Now let us consider for the first element, that is for the first element, tau 1 we have G1 is equal to 7 into 10 raised 4 into 50. That is the radius, that is the first one, which is having a diameter of 100 mm. Since the diameter is 100 mm, we will consider the radius as 50 mm and the length as 200 mm. And for considering this one, we have the angular displacement. Theta 1 is 0 because theta 1 is 0 because it has been fixed, and we have calculated theta 2 that we need to represent here, that is plus 1.162 into 10 raised minus 9. Solving this equation, we have the shear stress in element 1 is equal to 2.03 into 10 raised minus 5 Newton per mm square, that is 20.3 Newton per meter square. This is the stress developed in the element 1. Similarly, what is the stress developed in element 2? In element 2 also we can represent the shear stress equation, that is tau 2 is equal to G2 R2 and divided by L2 into theta 2 minus theta 1. In the second equation, that is theta 2 minus theta 3, we can represent this one, and that is one where G is 7 into 10 raised 4 and R is the radius of the second shaft element, that is the second element, that is 25, and length of the second element, that is 400, into theta 2 is 1.162 into 10 raised minus 9, and theta 3, consider this as theta 3, consider this value as theta 3. Theta 3 is minus of 1.050 into 10 raised minus 8. Solving this above equation, we have the torque, the shear stress in element 2 as 4.085 into 10 raised minus 5 Newton per mm square, or in terms of meters we can write it as 40.85 Newton per meter square. So hence we have solved what is the deformation, the angular twist, that is the angular twist in the element. So we have determined the angular twist theta 2 and theta 3, and along with this one we have determined what is the shear stress developed in element 1 and what is the shear stress developed in element 2. And this is the problem. In the next class we will also continue with the different problems which are subjected for a different, what you call as a combined loading of twisting as well as the axial loading. And for the next class we will be moving with the end of the 2-3 problems, and we will wind up the topic on analysis of shafts. Thank you.